Hello, everyone. Before we begin going through chapters 2 and 3, let's go ahead and start with a Hail Mary. In the name of the Father, and the Son, and the Holy Spirit. Amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou among women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. All right, so today we are going to go through chapters 2 and 3. We just went through chapter 1 last time we were together, and in that chapter we discussed how we got to where we are today in terms of mathematics and standards. And so today we're going to continue to lay that foundation for what we will learn in the future. And so we are going to talk about first exploring what it means to know and to do mathematics. And then in chapter 3, we're going to look at what it means to teach through problem solving. So first, we are going to look at what it means to do mathematics. And I think we all kind of have our own ideas of what it might mean based on our own experience. And that might be, oh, well, to do the math means to solve an equation, or to do math means to find x. And I think those things are certainly part of what it means to do mathematics, but I think that they are missing out on really the heart of what it means to do math. And so math actually is the science of patterns, and oftentimes it's not really thought of in that way. And so to do math really means to engage in the science of patterns and order in a variety of ways. So first, through generating strategies for solving different problems. Also by applying those approaches and seeing if they lead to solutions, and then checking to see whether your answers make sense. In other words, seeking out patterns and order within a situation. And as you hear about these three parts, this is where I think you can see how we can refer to science, we can refer to math as a science. You might have some fond memories of being in science class in elementary school, and you have to come up with a hypothesis, and then you perform an experiment, and then you look at your results to see if your experiment did in fact prove or disprove your hypothesis. And in a lot of ways, we have to do that in mathematics, right? So here's, say, I present you with a pattern, right, or a problem. And part of, if I were to make an analogy to the science experiment, well, you coming up with a hypothesis in this situation would be like coming up with a strategy to solve the problem. And then, of course, you're going to apply your strategy to see if it works. Did it actually solve the problem? Was it smooth? Will it work if I give you another type of problem that's similar but different? And then to check to see if your answers make sense, to see if that hypothesis can actually help you with things in the future. And so we can see here that math, it's really much more than just solving a problem, but it's really the whole process behind coming up with that strategy, testing it, and then seeing what we can learn from our answers. We have a wide variety of verbs that we can use for doing mathematics. We can categorize them into two smaller categories. On the left-hand side, you see we have our lower level thinking verbs, and then on the right-hand side, we have our higher level thinking verbs. And those verbs on the right-hand side, they lead to opportunities for higher level thinking, and they encompass those ideas of being able to make sense of what we're doing in math, or being able to figure out something. And these verbs might actually look familiar to you because they are from the higher levels of Bloom's taxonomy. If you're not familiar with Bloom's taxonomy, it's basically a list of different words that are grouped into different levels, and they're words that indicate different levels of understanding, different levels of thinking, and different levels of comprehending. So for example, something that's on the lower end of Bloom's taxonomy might be a verb like identify, whereas something that's a little bit higher up could be the verb compare and contrast. Right? And so we want to use those words, especially on the higher level thinking side, and we want to use activities that incorporate those words because in doing so, we will help our students to take their math thinking and their math ideas to the next level. And that will happen in a variety of ways. So one, we can help our students connect what they're learning to previous material. With those verbs, we'll also be challenging them to respond with information just beyond the required response. For example, I'm thinking of the higher level thinking verb that says explain. Right? And so you could have a problem that says, say, add these two fractions together. And that would be one thing, but it would be a whole nother level if you were to tack on that word explain. So find the sum of these two fractions and then explain how you did it. It's stretching the students to go beyond just that task that's in front of them. And then it also challenges them to conjecture or to predict. And that might be coming from, in particular, that word there, that verb there that says to formulate, right? And so maybe think about what would happen in the future if this pattern continues, different things like that. And so this is not to say we don't use those lower level thinking verbs, but it's important that we don't stop there, that we maybe start with those lower level thinking verbs, but then we challenge our students with those higher level thinking verbs in order to stretch their mathematical thinking. In this course, you will be asked to do a lot of mathematics, and I would say you will be asked to do math mainly in 4 different ways. The first 2 ways are here on this PowerPoint slide. So one way is by searching for patterns. And so let's take a look here at this activity that's on the slide. And so here we see a circle of numbers, and it looks like they're jumbled, like there's no necessarily a particular order that we can see to them right away. And so this says to begin with a number and to add or jump a fixed amount from that number. So for example, start with 3. So let's go ahead and we'll point to 3. So that's where we're going to start. And then we're going to jump by 3s. So 1, 2, 3. So the next number is 2. If I jump by 3 again, the next number is 1. If I jump by 3 again, the next number is 0. If I jump by 3 again, the next number is 9. Jump by 3 again, the next number is 8. And I think we're starting to see the pattern here. And so the pattern that we notice is that whenever I start at 3 and I jump around the circle in a clockwise manner by 3, it looks like the number is going to decrease by 1 each time, with the caveat of after 0, we go down to 9. And so that's an example of doing math, right? We just did math there together where we investigated by searching for a pattern, right? We followed what the activity says, and then we went around and we noticed that, okay, yeah, the pattern is that the numbers are going to decrease every time. So that's an example of doing mathematics. Another way you're going to be asked to do math is by analyzing different situations. And so the situation here on the right-hand side, it's about Ron's Recycle Shop. And it says that at Ron's Recycle Shop, he started the shop when he bought a used paper shredding machine. His business was good, so Ron bought a new shredding machine. The old machine could shred a truckload of paper in 4 hours. The new machine could shred the same truckload in only 2 hours. How long will it take to shred a truckload of paper if Ron runs both shredders at the same time? And this activity is actually one that's going to show up in your lab for this week. And so we're going to hang tight on looking at that activity for now. Right, so those are the first 2 ways you could be asked to do mathematics, searching for patterns and then analyzing a situation. 2 other ways in which you will be invited to do math include generalizing relationships and experimenting and explaining. The activity on the right is actually also on your lab, so we won't necessarily look at that one in detail today, but let's go ahead and take a look at the activity on the left. And so this one is about generalizing relationships. And this is actually a huge aspect of math, especially moving forward after elementary school, going on to middle school, high school, and even beyond that. So this says addition. When you add 7 plus 7, you get 14. When you make the first number 1 more and the second number 1 less, you get the same answer. 8 plus 6 equals 14. Is this always true? Why or why not? I invite you to pause the video right now to maybe think through this for yourself, and then go ahead and hit play when you're ready to hear what my thoughts are. So in terms of adding, right, if you were to take 1 more than the first number and 1 less than the second number, will you always get the same answer? That is going to be always true, because if you think about a sum, right, you're just adding the total amount of things you have together. And so if I add 1 more to the first, but I'm also taking 1 away from the second, I will always have the same amount there, because the adding and taking away from essentially will cancel each other out. So that will always come out to be true. On the next slide here, I have another example for you about generalizing relationships. and I want you to try it. So this says some people say that to add 4 consecutive numbers, you add the first one to the last one and multiply by 2. Is this always true? Show it. And so once again here I invite you to pause the video, maybe try to come up with some examples yourself to see if you can make sense of if this will be true always or not, and then go ahead and hit play when you're ready to see how you did. So to see if we can come up with some sort of relationship here, I think it's best if we think of an example. So I'm going to write down 4 consecutive numbers, and I'm just going to stick with 1, 2, 3, and 4. Okay. And let's think about the sum. So we want to compare the sum if I were to find it the traditional way, which is just to add up all the numbers. I want to compare that to if I were to add the first and the last and then multiply by 2. So just the traditional way, if I were to add 1 plus 2, that's 3. 3 plus 3 is 6. 6 plus 4 is 10. So this is a sum of 10. But now let's see if we do the method that's presented to us. So if I add the first and the last together, 1 plus 4 is 5. And if I multiply that by 2, I get 10. And so here, it looks like that does in fact work. But let's go ahead and try one more set of numbers to see if it works again. So I'm going to pick another set of 4 consecutive numbers. So I'm just going to use 2, 3, 4, and 5. And if we add all 4 the traditional way, so 2 and 3 is 5. If I jump, I have 5 and then another 5, which is 10, and then 10 plus 4 is 14. And so let's go ahead and add the first and the last. So 2 and 5 is 7. 7 times 2 is 14. And so once again, I see that those numbers do in fact match up. But let's try one more. I'm going to jump to a different set. So I'm going to use 4, 5, 6, and 7. So again, if I add the traditional way, well, I notice 4 and 6 is 10, 5 and 7 is 12. And so I get 22. And if I add the first and the last, 4 and 7 is 11. If I multiply that by 2, it's also 22. Okay. So it looks like we've tried 3 different sets of numbers, and each time this has come out to be true. Now, in mathematics, in order to generalize a relationship, something like this, right, where we're noticing that in order to add 4 consecutive numbers, if I just add the first and the last and I multiply them by 2, it's going to match up for the overall sum, right? To say that something like this is always true, you technically would need to show that it works for every possible combination of 4 numbers. However, that is something that's, I would say, a little bit more advanced for the students that we're working with. And so just from something like this, I've shown that this works for 3 different types of examples. And so here we would be able to generalize this relationship and say that, yes, if I were to add 4 consecutive numbers, I can simply just add the first and the last and multiply it by 2, and it would be the same as finding the sum of all 4. So we just talked a lot about what it means to do mathematics, and we learned that that can happen in a variety of ways, like by looking for a pattern, being able to explain something. Right? And so now we're going to talk a little bit about what it means to understand mathematics. And I think this, again, is a big misconception for a lot of people, right? Some people think, oh yeah, I know what to do, therefore I understand. But it's a lot more than that. And so here we say that understanding is the measure of quality and quantity of connections between new ideas and existing ideas. And contrary to popular belief, knowing does not necessarily mean understanding. So for example, a student may know something about fractions, but they might not understand them. And so further with this, we can kind of break understanding down into 2 smaller types of understanding. Right? And so the first here is this instrumental understanding. Instrumental understanding is when a student does something, but they don't understand why. They just know what to do. In contrast to that, we have relational understanding, which is when a student knows what to do and they know why to do it. So to give you an example to illustrate the difference between these two types of understanding, let's say the task here was to add fractions together. Right? So a student who is at the instrumental understanding phase would simply know how to add the fractions, right? I add the numerators, and I need a common denominator, I add the denominators. And that's kind of where the understanding there would stop, right? However, somebody with relational understanding would know that, okay, to add fractions, I need to have a common denominator. I know how to find the common denominator, but then they would also know why it's necessary. So it's really emphasizing the why behind things. And so our role as educators is to help our students transition from that instrumental understanding to that relational understanding. And that's why we have those verbs, right, for doing mathematics. It's why we should be challenging our students by using those words from the right-hand side, the higher level of thinking, because it will really help them transition from this instrumental understanding to a deeper, more relational understanding. Now, when a student shows high levels of understanding, we might say that that student is mathematically proficient. And when we say that, mathematical proficiency, it really refers to 5 interrelated, interwoven strands, and those are what you see illustrated on the slide here. So the 5 strands are conceptual understanding, procedural fluency, strategic competence, productive disposition, and adaptive reasoning. And so we'll dive in a little bit to each of these different aspects or different strands. So first would be conceptual understanding. Conceptual understanding represents a comprehension of the mathematical concepts, operations, and their relations, right? So let's say I can kind of give an example to help us illustrate these strands. So let's say you were helping your students solve one-step equations, right? And so a student who has conceptual understanding would know that to solve a one-step equation, I need to use an inverse operation. So for example, if I gave a student x plus 1 equals 3, right? If they're at that level of conceptual understanding, they would know that they would have to take away that 1 to isolate the variable. Okay. Next, we have the strand of procedural fluency, which is a skill in carrying out the procedures flexibly, accurately, efficiently, and appropriately. So back to our solving an equation example, right? A student who has procedural fluency would know what to do to solve the equation, and they would actually then be able to go ahead and do it, to perform those operations to get the variable by itself. Next, we have strategic competence, which is the ability to formulate, represent, and solve mathematical problems. And so here I can kind of think of maybe a word problem, right? Where not only does a student have to kind of read through the words to figure out what information is important, but then they also have to write an equation and then go ahead and solve it from there. So you can kind of see how these strands are starting to build off of one another. The next one is a productive disposition. And this doesn't necessarily go down to a student knowing how to solve any particular problem, but this one, and in particular the fifth one, adaptive reasoning, more so go towards the student's overall attitude towards math. So a productive disposition is a habitual inclination to see mathematics as sensible, useful, and worthwhile, coupled with a belief in diligence and with one's own efficacy. So it's kind of twofold there, right? A productive disposition means the student knows that math is important, and they also believe in their own ability to do mathematics. Lastly, we have adaptive reasoning, which is the capacity for logical thought, reflection, explanation, and justification. And so that's, do you know, are you able to explain what you just did there? And can you think about what to do depending on the situation there? And so it's really important that our students grow in all 5 of these strands together, and that leads to their mathematical proficiency. Now, a really important aspect in getting our students to reach higher levels of thinking in mathematics is the ability to problem solve. And a definition I could give to problem solving is knowing what to do when you don't know what to do, right? It's being able to think on your feet and being able to know in any particular situation what you should do, especially when you're stuck. And in particular, I would say that there are 3 ways to use problem solving in the mathematics classroom. And those are here outlined on the slide. So the first is teaching for problem solving. which is just teaching skills and then providing problems to practice those skills. So explain, practice, and apply, kind of that cycle over and over again. This, I would say, we see a lot in our mathematics classrooms. Then we have teaching about problem solving. And there's this person named Polya, and they define a 4-step problem solving process, which is to understand what the problem is asking, devise a plan, carry out that plan, and then look back and reflect to see if it helped you accomplish what you needed to. And then we have teaching through problem solving. And this is teaching content through real context problems, situations, models, and exploration. If any of you have ever heard of inquiry-based learning, that's kind of what we mean by teaching through problem solving. And these 3 ways of using math problem solving in the classroom are kind of at different levels. And I'd say the level we want to be at is being able to teach through problem solving. I would say, like I said, teaching for problem solving is probably what occurs the most in our classrooms. But this is not always effective because it gives the learner a more passive approach, right? Teachers are the ones who are saying, this is how you should do it. This is what information is relevant. And now go ahead and see if you can do that after me, right? Now, there's not necessarily a problem with that, right? But it's a problem if that's kind of the method that's being used all the time, right? I think teachers usually think that this method is good because it usually leads to preventing student struggle while also saving time. But something that we have to learn to be comfortable with as educators is actually our students struggling, because it's struggle that actually leads to learning, right? If something is difficult, but then I learn to overcome it, well, I'm going to remember that experience a lot more than if something was really, really easy for me to do, or if something was kind of presented to me in such a way that I didn't have to struggle, right? So students actually learn best by doing math engaging, or by engaging in math challenges. But those challenges have to be at a level that's accessible to your students, right? So not being shown a step-by-step process, but also not being given something that's too challenging, that's out of reach. Right? And so this is the challenge for us as educators, right? How do we learn how to teach through problem solving in a way that's appropriate for our students? And that's what we're going to talk about a little bit more. So when thinking about how to implement teaching through problem solving in your classroom, one way you can do that is by having your students do what we call worthwhile tasks. Right? And so worthwhile tasks, they're problematic and they pose a question to students. Oftentimes they are relevant and applicable. So maybe it involves a situation that students were just involved in, right? So maybe it's fall and you went on a field trip to the apple orchard. So maybe your problem that you present to students has to do with the apple orchard, right? There are also tasks that are problematic and they stimulate thinking and problem solving, right? So it's not as simple as, Johnny had 4 apples and Susie had 3 apples. How many apples do they have all together, right? It's something that's more stimulating and leads to more thinking, right? These tasks also have no prescribed or memorized rules or methods to solve, right? So in other words, they're flexible. They give students the opportunity to figure out the answer in a variety of different ways. They do not have a perception that there is one correct way to solve it. Right? Again, that flexibility of there's not just one way to do it, there could be multiple ways. There are also tasks that involve higher order thinking and are cognitively demanding. However, they do offer boundaries or constraints, so there is still maybe some guidance, but plenty of room is left for exploration. They stimulate discourse and collaboration, right? Which means that they encourage the students to work together, to work with one another, to use each other's ideas to accomplish the task. And then they also have the potential to provide new mathematical insights or knowledge, right? They always help students to learn something new. And so if a task can have a lot of these different aspects to it, well, then it would be a great task for your students to learn through problem solving. And I would say it's important that you either have written these down or copied them down in some way because they might show up again. All right, so what about drill and practice? I would say drill and practice is something that probably a lot of us have gone through, right? Something like multiplication tables, right? Doing tasks over and over and over and over and over again for the sake of drill. But I think it's first to be important that we kind of understand the difference between practice and drill. So first, practice refers to different tasks or experiences spread over numerous class periods, right? So that's the key there, key difference, spread over numerous class periods, but each is addressing the same basic idea. Okay, so kind of over a longer span of time. Right? However, drill refers to repetitive exercises, so many times in the same day. Repetitive exercises designed to improve skills or procedures already acquired. Right? So again, drill is not entirely bad. It's still good for some things. In particular, I'd say it's appropriate for recalling basic facts, right? Like your addition facts, multiplication facts, but maybe in limited doses, like maybe only for 5 or 10 minutes at a time, right? It does help to improve procedural knowledge, but not necessarily conceptual knowledge, right? Looking at the slide here, going back to kind of the difference between practice and drill, right? So we say practice is the opportunity to help your students develop conceptual ideas and more elaborate and useful connections. Right? In practice, they also have the opportunity to try out alternative and flexible strategies, and they encourage more students to understand. Through practice, students get the message that mathematics is about figuring things out. Right? Now, again, with drill, it still has benefits, as we discussed a little bit already, right? It can provide students with increased facility with a procedure that's already learned, right? So it helps them to do it quicker, more efficiently. It's also a great way to review facts or procedures for retention. So again, like multiplication tables. However, it does have some limitations, right? It focuses on a singular method, right? So it says this is the only way that it should be done, and this is the only correct way, right? However, that might not always be the case. It excludes flexible alternative methods. It does kind of give a false appearance of understanding, right? So, for example, a student might be able to memorize and the whole multiplication table, right? But they might not know or understand exactly how those facts came about. And it also does lead to a rule-oriented view of mathematics. And so, again, drills still have a place, but I think the key here is to keep your drills short and to connect procedures to the related concepts. And that's really the important part, is to not have your students learn through drilling, but to offer a different explanation method first, maybe then incorporate some practice, and then use drill just as a way to expound upon what they've already learned through different methods, right? So keep drill short and always connect it to procedures. Otherwise, it can negatively affect your students' perceptions and their motivation. One more important aspect of helping our students learn through problem solving is productive talk for supporting classroom discussion. Right now, classroom discussion, I know that sometimes that can be a challenging thing, especially depending on the grade level of your students. And so this slide here, it aims just to give you some tools, maybe some different ways of asking questions that might lead to helpful discussion amongst your students. Right. So the first teacher move, is called revoicing. This move involves restating the statement as a question in order to clarify, apply appropriate language, and involve more students. It is an important strategy to reinforce language and enhance comprehension for ELL. So as an example of revoicing, you could say, you use the hundreds chart and counted on, right? Or so first you recorded your measurements in a table, right? You can see there it's just encouraging your students to re-explain what they did to you. Right. Another move is rephrasing. So in rephrasing, you ask students to restate someone else's ideas in their own words. And this will ensure that ideas are stated in a variety of ways and encourage students to listen to each other. So again, another example of what you could say as a teacher, you could say, who can share what Ricardo just said, but using your own words. Right. So this, again, not only makes sure they're listening to one another, but then it does open up the whole entire class to maybe different ways of understanding. The next one is reasoning. So rather than to restate, as in talk move number 2, this move asks the student what they think of the idea proposed by another student. So maybe, do you agree or disagree with your classmate? Why or why not? So again, you can see how that can lead to that higher level thinking. Then we have elaborating. This is a request for students to challenge, to add on, or to elaborate or give an example. It is intended to get more participation from students, deepen student understanding, and provide extensions. So maybe saying something like, can you give an example? Do you see a connection between Julio's idea and Rhonda's idea? Or what if? And then lastly, we have weighting. Ironically, one talk move is not to talk, and this is definitely something that I would say is challenging, can be challenging for us as students, right? Because we feel like we have to be talking, or that quiet is not a good thing, but it is, right? So here, quiet time should not feel uncomfortable, but should feel like thinking time. If it gets awkward, ask students to pair share and then try again. Right. So maybe saying something like, this question is important, let's take some time to think about it. And then just as the teacher being okay with some silence, right? That means kids are thinking, right? So now some final thoughts, right? Questions are important in learning about student thinking, right? Asking a simple question, by asking a simple question, you're able to figure out where a student is at, right? Or by asking a question, you can challenge a student conclusion, or you can help them to extend their inquiry, right? Or generalize patterns, generalize something they saw a classroom do. Now, it's also important how you respond to these answers, or how you respond to student responses, right? So, in terms of correcting or confirming a correct solution, right, rather than using one of these talk tools, you lose an opportunity to engage students in meaningful discussion about mathematics, and thereby limit their learning opportunities, right? So, in other words, rather than just saying, yes, Johnny, your answer is correct, right? Instead of confirming that right away, right? This is your opportunity as an educator to maybe use one of these 5 talk moves, right? Because that is what would stretch their thinking, right? And so as teachers, I think we always struggle with, well, how much do I tell my students? How much do I guide them? And research has been done, and it does suggest that there are 3 things that teachers do need to tell students. Right? One is mathematical conventions, so like symbols, right? So like equals means is the same as, right? Or this symbol is the equal sign, it means is the same as. Also terminology and labels, so making sure you're being clear about vocabulary, different things like that. It's also important that we tell students alternative methods to maybe accomplishing a task. Right? An important strategy does not necessarily emerge naturally from students, but maybe should be introduced as another way, but not the only way. And the last thing teachers do need to communicate is clarification or formalization of students' methods, right? In other words, to help students interpret their ideas and point out related ideas, right? And so, again, just to summarize here, right, we've talked a lot about what it means to learn and to do mathematics, and what it means to understand mathematics. And as teachers, we have an important role here, where we really need to facilitate experiences for our students that not only help them to understand and to know what to do, but to really branch off and expand their thoughts, right, to bring them to higher levels of thinking. And so here, to sum it up, right, whenever we talk to our students, or whenever we engage them in discussion, right, again, it's important that we're always aiming at hiring their level of thinking, and not necessarily just ending with confirming the correct answer, right? And so whenever we go to do lab 2, when we're all together, right, you will have the opportunity to engage in a lot of these experiences. And so, right, I look forward to seeing you guys during our next class. Take care. God bless.